We'll see you in a second or two. All right, so you're back now. So looking at example A, shuffle a deck of cards, turn over the top card, put the card back in the deck and shuffle again. Repeat this process 10 times. Let X equal the number of aces that you observed. So is this binary? Yes, because either the card is an ace or it's not. Is each trial independent? Yes, because we are putting the card back in the deck. Do we have a fixed number of trials? Yes, it's 10. And is the probability of success going to be the same on each trial? Yes, it is. There are 4 aces in the deck and 52 cards, so the probability will stay the same. For B, choose 3 students at random from your class. Let Y be the number who are over 6 feet tall. So is this a binary? Yes, it is, because the person is either over 6 feet or they're not. Is it independent? It is not independent because each trial we don't replace the student. Okay? So each trial is not independent because we don't replace the student. All right, example C. Flip a coin. If it's heads, roll a 6-sided die. If it's tails, roll an 8-sided die. Repeat this process 5 times. Let W equal the number of 5s you roll. Oh, and before we continue on with this, I forgot to mention that, of course, as soon as we get one of our 4 requirements that is not satisfied, then we say this is not a binomial setting. All right, so for example C, this is binary outcomes, right? Because we're looking for whether it's a 5 or not a 5. Is it independent? Yes, it is. What happens this trial is not affected by what happened the previous trial. Are the number of trials fixed? Yes, it is. We are repeating this process 5 times. And is the probability of success the same on each trial? And in this case, it's not. And that is because if I roll a heads, I'm going to be rolling a 6-sided die, so the probability of a 5 is going to be 1 out of 6. If I roll a tail, the probability of a 5 with an 8-sided die is going to be 1 out of 8. So the probability of success is not the same. So therefore, this is not a binomial setting. Example D. Genetics says that children receive genes from each of their parents independently. Each child of a particular pair of parents has a probability of 0.25 of having type O blood. Suppose these parents have 5 children. Let X equal the number of children with type O blood. So, do we have binary outcomes? And yes, we do. They either have type O or they don't have type O. Are the trials independent? Yes, they are. The fact that your older siblings do or do not have type O does not affect you. N, the number of trials, is fixed in advance. Yes, they have 5 children. And S, is the probability of success the same for each trial? Yes, it is. And so this is binary settings, a binary setting. All right, moving on to our next example. And of course, if you have any questions, feel free to pause the video, go back, look at the textbook, and then if you're still not sure about something, jot down a note so that you're ready for class time. Example 3. Consider tossing a biased coin 4 times and recording the number of heads. Create a list of all possible outcomes of this experiment. Now, the order matters when we're creating our list of the possible outcomes. So we could have heads, 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 and heads. We could have head, 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 tail, head, head, tail, head, head, tail, head, head, and then continuing on, tail, head, head, head. So now I've gone through all the ways of getting all heads, all the ways of getting one tail. Now we'll continue and add 2 tails. And you'll notice that I'm doing this systematically so that I don't miss anything. And that's it for 2 tails. And the last one is head, head, tail, tail. And we have a total of 16 different possible outcomes. So we're going to move on now and define x to be the number of heads that you observe in the 4 tosses. Now, this is a biased coin toss, and so our probability of receiving a head is not 0.5, but is rather 0.6. So we have more chance of getting a head. Now, if we had done simply a 50%, then each outcome would have been equally likely, and we could have simply looked at the number of outcomes that we have for each one. And there is one possible outcome at 0. There are 4 with just 1 head. There are 6 with 2 heads, 4 with 3 heads, and 1 again with 4 heads. However, this time we do not have an equal weighting. So when we do this, we have to say that the probability of getting no heads, which is where we have all t's, this one, is going to be 0.4 times 0.4 times 0.4 times 0.4. So it's 0.4 to the 4. The probability of getting exactly 1 tail, of exactly 1 head, well, the probability of getting 1 head is 0.6, and then for each of the other 3 flips, the probability of getting a tail is 0.4, and there are 3 of them. And there are 4 ways of getting that. The probability of 2, here we have probability of heads, 2 heads would be 0.6, and 2 tails is 0.4. 3 heads, 0.6 to the 3, and 0.4 to the 1. And the probability of 4 heads is 0.6 to the 4. So if we look at our probability distribution, 0, 1, 2, 3, and 4. The probability of x, meaning the number of heads out of the 4 rolls, as we calculate these out, we get 0.0256, 0.1536, 0.3456, 0.3456 again, and 0.1296. And when we add these up, they do add up to 1. Okay, so just a reminder that the coefficients, which were 1, 4, 6, 4, and 1, and you can maybe think about those numbers and how they relate to each other, are the number of ways that that outcome can occur. So for C, is the probability distribution in part A a legitimate probability distribution, and why? We've alluded to that already, and that was that the sum of the probability of X equals 1. So remember, when we add up the 5 numbers there, they did add up to 1, and all the probabilities are positive. So the answer was yes. All probabilities are positive. Now, we'll go over what the binomial coefficient is and how it's used. To see where the formula comes from, you will want to look at my mini lesson on combinatorics for the background. That mini lesson is background information to help you understand where the things come from, as opposed to something that will be tested in this course.